Hello. So in this problem we have a C transform and we need to find the inverse C transform, and this is typically going to be done by inspection. So if you recall, the C transform was given by the sum from n equals minus infinity to infinity x of n c to the minus n. And so you have a signal in n transforms it to a polynomial in C, where you have both the location of the amplitudes, you have the amplitude information of that signal as well as the location of that particular sample or amplitude. So in this case, what we have x of c equals 1 minus 3 c to the minus 1. We see that we don't have any c to the minus 2, so it's helpful. 0 c to the minus 2 is helpful to indicate it, plus 4 c to the minus 3 plus 0 c to the minus 4 plus, or actually minus 2 c to the minus 5. And with this, it is trivial to find which signal x of n will produce this signal, right? And so it is delta n minus 3 delta n minus 1 plus 0 delta n minus 2 plus 4 delta n minus 3 plus, I'm just going to go minus 2 delta n minus 5. Or the vector x 1 minus 3 0 4 0 minus 2. So what you see is that when you did the C transform of this vector x of c, and you came up with what we saw there, 1 minus 3 c to the minus 1, remember this is 0, 1, 2, 3, 4, 5 in terms of n, what we get is the amplitude and the location, plus 4 c to the minus 3 plus or minus 2 c to the minus 5, as you can see here, 2, 5. Now, as we mentioned, this polynomial, when you find the roots, meaning you equalize it to 0, this is finding the roots, is valuable for analysis of signal properties as well as system properties. If that signal, if this happens to be an impulse response, h of n, imagine that those were the filter coefficients of an FIR filter, the B coefficients. So you have something like this, h of n equals, in vector form, 1 minus 3, 0, 4, 0 minus 2, and you want to say, what type of filter is this? Finding the system function as we have here, 1 minus 3 c to the minus 1 plus 4 c to the minus 3 minus 2 c to the minus 5. This, when you have any rational LTI system transfer function with a numerator in C and a denominator in C, the zeros, the roots of the numerator, and the poles, the roots of the denominator, gives you information about the system. Also, that system function, that transfer function, if you evaluate it for C equals e to the j omega hat, and so you end up with 1 minus 3 e to the minus j omega hat plus 4 e to the minus j omega hat times 3 minus 2 e to the minus j omega hat times 5. This is the frequency response. This is equivalent to evaluating the discrete time Fourier transform, which is given h of j omega hat as the sum x of n e to the minus j omega hat n for n equals minus infinity to infinity. And what you are doing, of course, if you are looking at the C-plane, real and imaginary, you have the unit circle here. This is your frequency. This is e to the j omega hat. These are low frequencies. This is 0 or 2 pi. These are high frequencies, pi or fs over 2. And what we are doing is traveling around the unit circle here. So, to recap, the C-transform is a technique very useful for system analysis. And it's going to enable us to transform a signal, like something like this, in this case it's an impulse response, I just put it, if this is an impulse response, into a polynomial, what you have here, and the polynomial contains both the sample amplitude information, the 1, 3, minus 3, 4, as well as in the exponents, the location of those samples. And that polynomial turns to be very important. Surprisingly, that polynomial and the values that make that polynomial when you have an equation equal to 0, those values, those roots, those values of C are useful. In the context of an FIR filter, those zeros tells you the places, wherever they are located, okay, where you're going to be pulling the frequency, if they are in the unit circle, to 0, or if they are close to the unit circle, also they're going to pull down that frequency. Okay. Once we look at IIR filters, we put poles, and of course also here the poles, we are going to see whether the system is stable by looking at the location of the poles. If they are within the unit circle, the system is stable. Now, you can use MATLAB and the function C-plane to find the C-plane where you put B and A coefficients to find the to plot the C-plane. With that, in the next activity, what we are going to see is that the system function is a complete characterization of the system, and that actually these values of the signal C to the M is an eigenfunction of LTI systems. Okay? The same way that e to the st in continuous time was an eigenfunction. Thank you.